Okay, so we've seen how a game table can have a row that's dominated, weakly dominated by another, as R1 weakly dominates R3 in table 5.8, and yet R3 can still contain a point that's in Nash equilibrium. Now let's look at problem 4 on page 132. Marisha?
Suppose in game G, row R is strictly dominated by some row S. That is, every entry in S is greater than its correspondent in R.
Okay, so here's what we've got. We've got a situation in which row has multiple rows. One of the rows, R, is strictly dominated by row S. So every single entry, no matter how many there are, on S is a number on row's utilities that's strictly greater than the number on row R. So this one is greater than this one, this one than this one, this one's greater than this one, all the way to however many columns there are. So now, what's the question?
Can R be half of an equilibrium pair for G?
Can any of the entries, any of the points here, be half of an equilibrium pair on a strictly dominated row? The answer to this question is no. Because you can see this from a number of reasons. One, first of all, if they get on any point in this row on row R, row will have unilateral reason to switch from that particular point to that same point in that same column on S, because the point on S will be greater than the point on R. It's also the case that none of these could be a mini-max strategy, right? You can reason that out as well. Also, this will not be row's security level, because row will always be able to do better with the worst outcome in S than is going to do better with the worst outcome in R, because of the strict dominance that it attains here. So when it comes to weak dominance, it's possible for a weakly dominated row to have on it a part of a Nash equilibrium pair. It is not possible for a strongly dominated row to have on it a point that's part of a Nash equilibrium pair, because whatever the point is, the row will do strictly better by unilaterally changing from R to S. And as we mentioned, and as Marisha mentioned to me, we also have the proof that we'll see a little later on, that equilibrium pairs always in multiple equilibrium pairs always have the same value. And notice that no place on row here is going to have the same value of S. So what I'd like for you to do now is, having looked at this and having tried the homework problems, make sure you have this down, because next we're going to move on to a strictly competitive two-person game that's much more interesting from the Nash equilibrium perspective, because none of the points by themselves are in Nash equilibrium. Nevertheless, these games have a solution, and we're going to see the fascinating solution they have, which raises a fascinating philosophical question I'm going to ask you to reflect upon. I also recommend that if you have time, find yourself the 2001 movie, A Beautiful Mind, and watch Russell Crowe play the mathematician John Nash in all of his quirky weirdness. See ya.